All right, time for another DraftPhysics.com. DebatePhysics.com also. But again, the debate is so broken. So Pyrrho has left a comment. Okay, nobody can draw anything. Nobody can show anything. There's no possibility of having some discussion about mechanics in some sort of realistic context where you understand the parts that are moving and what you're proposing as a possibility. All right, so this involves a discussion about, so we'll just, I'll make 9. Okay, yeah, 9 stairs. Okay, all right. And so you're going to take a weight. It might be 9, I don't know. And you're going to lift it. Okay, a height. Okay, so we're taking a weight and we're going to lift it a height. And we have the alternative of just launching it at a velocity that'll get it up to that height. All right, in one push. You know, you give it a velocity, it'll go a certain height, and it'll take a certain time. Now, in this case, we're going to say this takes 3 units of time. All right, to get to this height. Okay, and so it has 3, we could argue, units of velocity. But anyway, so we know that the velocity of the object, okay, it starts off very fast and it goes very slow, and so the time, okay, will be in this 3, 5, 1, 3, 5 kind of way. Let's see, do I want to, yes, yeah, it has to be 3 units of, so we're going 9 stairs, so 3 units of velocity. Okay, and 3 units of time. All right, so I guess I could draw that as this. This is 1 unit of time, will be this last little bit. Then this hunk will be 1 unit of time, and then this 5 will be 1 unit of time. So it's 1, 3, 5. All those are 1 unit of time fighting the gravity, losing energy to the gravity. And so if I go by the stairs, you can see that, okay, I'm going to be doing this 1 unit of time thing. So I'm going to do exactly the same thing. So I lift it up, and I'm only fighting the gravity for 1 unit of time. Right? Okay, you're getting the point here, right? Is that, well, yeah, this will be another unit of time. This will be 1 unit of time. This will be 1 unit of time. All right, let's just say there was 9 stairs. I could get up there, okay, and I'll have done 9 units of time where I'm fighting the gravity. So that's what he says is how the game works. All right, and that this somehow is the same energy as this. So lifting against gravity 9 times is the same work as just lifting against 3 units of gravity. And that's all there is. There's a, like I said, it's a time I don't know. They're still arguing it's not a time-dependent force. Well, that doesn't make any sense. So I would obviously say that this is going to be a lot easier to do 1 velocity 9 times versus doing 3 velocity once. Okay, that this will take less energy, a lot less energy. All right. So the context, that's the context. So we're arguing about this fact that you can you can make something more work by doing it slowly. Okay, and that quick movements, generally speaking, are more efficient when you're fighting gravity. So the quicker you get through gravity, the less work you have to do. The longer you take, the more work you do against the gravitational force. So it's the longer you're in the photons, the more suntan you get. The longer you're in the rain, the wetter you get. Simple argument. All right. So his sentence is this idea that somehow we can take advantage of the fact that it's more that you could drop something. Let's see. Okay. You could drop something slowly and then use the energy of the slow drop, the extra energy, to move something quickly up, and that you could make yourself a perpetual energy device. Well, I've argued the same thing against their theory, that it's perpetual energy to create free momentum. So if they have a theory that you can hit something that has 100 momentum, and then you can hit it into something and make it 300 or 300 momentum, that's free energy. Okay, and so their theory doesn't work, I think, quite obviously. All right, so the first thing he says, all right, so let's just deal with his stupid. So I'm saying, go ahead, show me how you can do it. All right, I'm not saying that I'm not denying that it's a truth that there's more energy to be gleaned from gravity by moving something slower in it. You know, letting it fall slower, you're going to get more energy out of it. But the problem is how do you convert that advantage into a launching, you know, in terms of converting the energy in one form into this energy in the other form, and that's the tricky part. So he says how you do it is to cock, he said cock, a spring with a slowly dropping device. Well, how do you do that? All right, so his argument is I could hit the, I could drop a 1 pound object on a spring, okay, and then somehow I can lock the spring, and then I can drop 1 pound again, and it'll go to 2 pounds. And I could drop it again, and I go 3 pounds. No, that doesn't happen. The spring has pressure in it. I can't put more pressure into it with repeated events. It's not going to help me any. I can't. So you explain to me how I put the energy into the spring. So you tell me how I take 4 drops, okay, of an object and convert that into 4 compressions of the spring, okay? Because the spring is saying I got 10 pounds of pressure going this way. I drop the first one, I lock it. It's 10 pounds of pressure. All I can create is 10 pounds of pressure by dropping these things. I can't create 20 pounds of pressure. I can only create 10. So I can't compress the spring. The spring just says, no, I'm not going to. You have to be stronger than me. You can't be the same pressure as me. If you're applying the same pressure, the spring's not going to move. You have to apply more pressure to make the spring move. You can't apply more pressure with the same mass. So how do I compress the spring with the slowly dropping object? Would be the first, you know, right from your first question. There's no point, right? So the rest of it's almost mute as a bit of conversation, because I don't know how I can do this. How do I put 4 small hammer blows into a spring? You tell me how I do that, then I'll do it. All right. Okay. Then you take the loaded spring to relaunch the 1 pound object to the top again. So again, I can't take it because I can't load the spring. So you explain how I load the spring, then I'll do that. All right, the spring only uses half its energy to do, so your system, that's your free energy per run. Right, and I'm arguing the same thing I can do with your silly theory of free momentum. All you have to do is move the spring from one side to the other. Yeah, well, that's always a trick too. Is, you know, every time you have to do something to the experiment, that's a liability. So the one I was thinking about, just since I'm here and I'm talking about it, is the car pulley thing, right? Okay, so you have a car, you know, the physicists do this one all the time, and they never do it the way I would do it, which is analyze how much impact energy there is from your falling object, right? So you have a mass here, and you just drop the mass, okay, and you can move the car. Now, obviously, how fast this falls depends on how heavy this is, right? So that's the trick, right? So the heavier I make the car, the slower the mass will fall. I think everybody can figure that much out. So it's going to be in the gravity a longer time, okay, falling. And so you would imagine that the car would have more momentum, all right? The heavier I can make it, the more I can get out of it. So if I make it a very light car that very barely interrupts this, well, then obviously it's going to hit here with the same impact energy because I didn't slow it down much. So what you're really just saying is we're going to measure the energy in 2 places, here and here. Now, the trick would be, is if I can get the car going fast enough, but like I said, how fast can I make it go if this is getting slower and slower? Well, it's in the gravity a longer period of time, the slower it goes. So yeah, I want to have the heaviest cart possible that still rolls. And the mass will be in the gravity the longest amount of time because I don't have a very fast velocity. And then I hit the ground with almost no force because it's going so slow. So I've taken all the force that this would have hit if it fell, and I've moved it into the car. So the car has all that force. And the simple experiment would be is, can I take this impact force, the car's impact force, and convert that into launching? So, I mean, you could think of it as a simple kind of a, you could almost say, okay, you could use leverage, you know, to try to force it up. So you have to put an inverter in there somewhere. You know, it hits this, and the force of hitting this, okay, moves a lever that would be this way, and it takes the mass and moves it up this way, right? So you hit this, it pivots on here, that moves this bar and moves the mass up. Okay, so, but then you got to say, okay, can I make this mechanism light enough where it's possible that I can lift the mass? And I guess my argument is that's the problem. You can't do that. But anyway, it's one way of understanding it, that's all. I'll throw it in there just as a thought experiment. Maybe it's doable with one of these other kinds of experiments, but I can't see off the face of it how it's doable. Now, how much you can compress this spring, that would be an interesting point, would be this impact into this spring. So let's say, okay, let's forget about all this crap and just say we're going to hit the spring now. And we have essentially the dropping energy, because we've slowed it down so much, we have essentially all the dropping energy going in a velocity. And so then we could compress this spring 4 pounds, let's say. All right. So maybe that's possible. Then we just have to move the spring down here to launch the mass back up. But all of that, again, so, I mean, it seems kind of easy to move the spring down, but moving the spring back up again is going to be the hard part. To reload your spring. So the weight of the spring is going to be a problem, because there's no way to get the spring back here if I put it down here. So we have to figure out some way where the spring can push the energy here, and it's the same as pushing the energy here. So again, we're back to a lever or something. So yeah, that won't work either. But anyway, so that's what the implication of it is. Okay, so my argument is all this is moot in some respects, because I'm going to argue if you accept these simple facts. So here's number one fact. Number one fact. So just deal with this fact and just explain to me how you disagree. So I made this lever on my porch, so it's a done deal, okay? And I'm hanging it from the top, which means if you think about what the lever's doing, all that's going to be happening is when it turns this way, it's going to put more. So when this side goes down, right? This side goes down, more of the lever is going to be on this side. So this side gets heavier, right? So when this side goes down, this side gets heavier. And when this side goes down, this side gets heavier. So all you're really doing when it oscillates, so there's no weights on it, we're just oscillating a lever, is all you're really doing is, for every motion you push down, the reaction force is because there's more mass on this side, so it pushes back down again. It overshoots, and it just keeps oscillating, okay? And the simple truth, so is once you understand this is the only energy, okay, this switching, the only thing keeping the oscillator moving is the fact that the mass is switching sides. So that's what's oscillating. A little bit of this material is moving over to this side moving over to this side moving over to that side. That's all there is. That's causing the oscillation. And so whatever you put on the lever is superfluous in some respects, but yes, so you can have, as I did the experiment, you could hang. So let's just make it more lever-like for the purpose of illustration. All right. So I hung a 1 mass here, 4 units of distance. Okay, 1, 2, 3, 4, yes. And a 4 mass here. Okay, so they just happen to be magnetic and made things simple. And so I had a 4-to-1 relationship, and then I caused the oscillation, and it works perfectly. Okay, and the fact is that this moves with 4x the velocity. So it's going 4 times the velocity that this is, 1 velocity here. And that's the equality. All right, so now we know if I drop a mass 4 times the distance, it only gets 2x the velocity. So we know a one mass falling twice the velocity is not going to equal this, okay? A one mass going 4 times the velocity. And that's what equals the 4 mass at 1 unit of distance. So, I mean, do you accept the idea here that it's simply saying the thing that balances, okay, is not twice the velocity with 1 mass, the thing that balances, okay, so a 4 pounds dropped 1 distance, okay, by the balances rules equals a 1 mass going, 4 times the velocity. So this is 1v, and this is going to have to be 4v, okay, 4 velocity. I mean, I could illustrate it as a distance, but it's not going to be 4 times the distance, it's going to be 16 times the distance. Okay, so you got to go a long way up to match the 4 mass to get 4 times the velocity. Right? 4 times the distance to get 2 velocity. To get 4 velocity, I have to go 16. Okay. So, way off. And what the lever does tell you that obviously I could just put a 2 mass here at twice the velocity, and that will equal the 4 at 1 velocity. 2 times 2 equals 4 times 1. So that will work, but this won't work. So, I mean, just explain to me where there's a mistake there, that in the rules governed by a lever or a balance, that's basically saying the oscillator has to have the same energy on both sides, and it's obviously having the same effect on both sides, that clearly a 1 at twice the velocity won't work. That won't balance. This will swing down because the 4 mass has more gravitational weight now, and it'll swing down, and this will swing up, and that'll be it. It's all over. There's no balance anymore. So twice the velocity isn't enough. There's no better way to say that, right? I mean, I could have illustrated this better, but I mean, that's the argument. So until you explain how the lever's lying, the balance, and it's not telling us the truth about what equals what, I'm going to argue you're still going to have to explain where you have evidence, okay, that 4 pounds dropped 1 foot is the same as 1 pound dropped 4 feet, because 4 feet is only 2 velocity. And 2 velocity, 1 times 2 is not going to be 1 times 4. So, yeah, maybe I'll end on that and just say, look, let's just deal with this argument first. Just explain to me where where I've made an error in this argument. Or show me a credible experiment, okay, where 4 pounds is dropped 1 distance and 1 pound is dropped 4 distances, and you're able to create the same force on a spring. Now, obviously, I would say the spring is going to retain the weight. Okay, we're talking about the instantaneous, okay, not what just sits on the spring, obviously. It's the impact force, which is best measured horizontally, I would argue, because then you take gravity out of it in terms of a standing weight. So you have a 4 pounds, okay, 4 pounds at 1 distance of height, okay, and then you have a 1 pound at 4 distances of height on a pendulum. They swing into their respective springs, and your argument is that they'll show the same compression. So at least you don't have to worry about 4 pounds hitting with the 4 pound weight and 1 pound hitting with only 1 pound of weight. I mean, obviously, the standing existing weight of the object would get in the way of the impact energy because it's still gravity's still acting on it. So at least with this experiment, you get rid of that defect, and you're purely measuring the momentum of the object. Okay, the momentum hitting the spring. You're saying those two things, okay, have the same energy. I say they have the same momentum. No, I don't say that. I don't say that at all. I say they have very different momentums, and there's no way they can compress the spring the same amount. All right. Yeah, so let's leave it there for now. So, you know, yeah, I'm just saying, in terms of contriving a free energy device, I think it's going to be a lot easier to take advantage of your theory, where I swing the pendulum into something and I get 200 momentums out. So it's just make it heavy enough so it just moves, barely moves. I'll get 199 momentum and I'll get 100 back. And so then it can hit again, and it can hit again, and it can hit again. And I can just keep putting objects in there, and so I can gain twice the momentum I started with 4 or 5 or 6 or 7 times. So I'll have so much extra energy that, of course, I could redo the experiment over and over again because I have gained so much momentum. And I could just use a lever with the thing that has twice the momentum, right? So I've created twice the momentum. I just have it smack into a lever, and then it can just shoot the other thing back. No problem. With the much higher velocity, the much lighter object at the higher velocity. All right. I guess I should draw theirs out and just point, but no, let's just stick to this. Just explain to me where there's a mistake here somewhere, and then we can move on from there. But I don't think you can. I don't think you can point out the mistake. So, because I don't think there is a mistake clearly. So anyway, we'll call that a video. I don't think he said anything else, right? Did I read the rest? Okay. All you have to do is move the spring from one side or the other, or if you store the energy in a battery. So again, how do you do that? See, I've thought of that, but I mean, every one of these electrical ways of moving something, you move something like a magnet in a coil, you don't have 100% efficiency. You know, you don't get, you put 100 momentums in, you only get, whatever, 50 watts out kind of thing. So it's not nearly efficient enough. If you just use a battery to cock again and fire the spring on the right. So again, this is the best you can do, right? So your counter argument is mushed based on false premises that can't be done. So what's the point? I mean, we're talking about hitting something 4 times or hitting something once, at a higher velocity. And you're saying a spring can collect both of those. It can't do it. Alright, so till the next time, and such, and so forth and whatnot. I think that's enough. Yeah, just a kind of a junk video, just for Pyrrho. I mean, he types this crap, and you're just like, oh, come on. You can't do better than that. Anyway, till the next time.